Great. So the last talk of today is going to be by Ravi Saripalli, and telling us about a collaboration at Tulane. Please go ahead.
Hey, Mark. Thank you very much. I'm Ravi Saripalli, working at Tulane University in the groups of Ryan Glasser and Dennis Bondar, and we'll be talking about the all-optical input-agnostic polarization transformer. This is a brief outline of my talk. I'll be first introducing polarization and the states of polarization in the Jones matrix formalism and how that ties in into quantum information sciences. And then move into what we're trying to achieve and the motivation behind this work. I'll be describing our experimental setups and the results, and finally summarizing the work. So polarization of light is defined as the direction of electric field of an oscillation of a light beam. And in the Jones matrix formalism, you define Stokes parameters. And the Stokes parameters are defined in such a way where I is the intensity of the light and the subscripts are the polarization basis, where you have the horizontal, vertical, diagonal, anti-diagonal, and right and left circular polarization basis. And in the Jones formalism, you can write the coherency matrix, and you can immediately see that this is quite similar to a density matrix of a qubit system. And similar to a block system, you can block sphere. You can actually define a Poincare sphere where you represent the different polarization states, and also the degree of polarization is defined as the ratio between the output polarization, the intensity of the polarized light as compared to the total intensity of the light. And this is somewhat similar to the purity when comparing to quantum information sciences. So there is a subtle difference between polarization and quantum information, but these differences can be accommodated by using appropriate factors and normalizations. And with this, and also you can access different polarization states by using wave plates. So half-wave plate keeps the polarization linear, but you can go around the sphere in this direction, accessing your horizontal, vertical, diagonal, and anti-diagonal states. And a quarter wave plate, when you rotate a quarter wave plate, you see that the polarization state takes a 8 shape on the Poincare sphere, and you can access the circular states. Basically, it converts your linear polarization to elliptical polarization. And also one more thing, sorry. So the DOP, the degree of polarization. So all the states on the surface of the Poincare sphere have a DOP of 100% or equal to 1. And if you access states inside the Poincare sphere, then the DOP goes down all the way from 0 to 1. So it can be, it ranges from 0 to 1. So I'll tell you how to access those states on the Poincare sphere. And so the states which are on the surface, or when the DOP is 1, we call them pure states. And the states which don't have a DOP equal to 1 or are inside the Poincare sphere, we call them mixed states. And so first, how do we access all the states on a Poincare sphere? So just a quarter wave plate or a half wave plate won't do. So there was a paper in 1990 where they say that, so basically this is an SU2 transformation. A complete SU2 transformation can be achieved by using 3 components, that is 2 quarter wave plates and a half wave plate. And so by using just three components, you can actually access all the states on the Poincare sphere, on the surface of the Poincare sphere. And now to access mixed states. So if you want to achieve states inside the Poincare sphere, in 2015, there was a paper where they spatially separate 2 beams. So they use a beam splitter, and they spatially separate the vertical and the horizontal components and combine them using another beam splitter. So this is an incoherent addition of the 2 states, 2 polarizations. And when you do that, you can achieve these mixed states or states within the sphere. And so with this, what we are trying to see is the correlation between optics and quantum technology. In this direction, a lot of work has been done where the, like the first Bell's test was also tested using polarization qubits. whereas in the other direction, we want to be able to use quantum technology to implement simple setups in optics to see these quantum information protocols. And so one such example is, so in quantum technology, there are cross maps which can map any density matrix to a particular density matrix. And this particular density matrix can be either a pure or a mixed state. And so in polarization, if we go back to polarization optics, so if we represent horizontal polarization as 0 and vertical polarization as 1, and we write a particular target polarization state in terms of the input states, and U0 is a SU2 transformation, then your cross map, there exists a particular cross map where you can take any input polarization and achieve a particular target polarization state. And for a simple example, if we define K1 and K2 in terms of 0 and 1, and if you substitute these states in the cross transformation, you see that you achieve a particular polarization state. So this is a many to one polarization transformation, and if you define these parameters in this form, and of course you can see that this automatically satisfies the cross map condition, and if you rewrite them in this form, you can actually achieve a setup that allows us to map all polarization states into a particular polarization state. And this need not be a pure state, it can be a mixed state, either a mixed input state or a mixed output state as well, which I'll show in the upcoming slides. So, of course, a linear polarizer does this, but the intensity of the output beam is governed by the Malus law. And there are two kind of technologies that exist to do this, to map all the polarization states to a particular polarization state. And one is using a feedback-based mechanism, so which is quite simple, where you have rotating wave plates, and some part of the obtained polarization is sent back to a linear polarizer. And governed by Malus law, the intensity dictates how much these wave plates have to rotate. And based on that, you can rotate those wave plates to attain a particular target state. And so this kind of feedback mechanism automatically does not work for single photons, because the single photons would be lost. And they do not work for ultrafast optics as well, because your timing circuits cannot be fast to accommodate for ultrafast pulses. There are other technologies based on nonlinear medium. So this particular example uses four-way mixing of an input state and the reflected beam. And because the target, I mean, when you combine the two, the beam has to have a particular polarization based on your input polarization. So if it was a left circular polarized, I mean, if it is in the top half of the Poincare sphere, then you would see that the target state would be on the top half of the Poincare sphere. And if the input state was in the bottom half of the Poincare sphere, you would see that the target state would be in the bottom half. So this is because the reflection is always, the reflectivity would always be less than 1. But if you can make this reflectivity greater than 1, then you can map all these input states into a particular state, and that can be done by using an amplifier, as they have shown in 2012. So the drawback of this setup is, one, it requires a nonlinear medium, and the second is that it can only be used for input pure states and target pure states. So you cannot have input mixed states and target mixed states, as in a cross mapping in quantum information sciences. So these are the drawbacks that I mentioned, and that brings us to the motivation of this talk. We would like, and so we present the all-optical input polarization, agnostic polarization transformer, or the AI-APT. So this is a very simple setup where for the first setup that I'm showing is for a target polarized state or a pure state. So you have any arbitrary input polarization, and the input polarization can be converted to different states on the Poincare sphere by using an SU2 transformation, as I had shown. And we convert the horizontal polarization back to a vertical polarization and combine the two vertical polarizations on a 50-50 beam splitter. So the state achieved here for any input polarization would be vertical. And of course, you can use another SU2 transformation to convert that onto any point on the Poincare sphere. So here when we see, so these are the different input states that we went in with, rho, and this is the target, this is the, we use a polarimeter to determine the target or the outcome of the setup, and which you can see is all vertical for any input state that you give. It's simple to see that. So here we have a vertical state, and if we combine a horizontal state using a beam splitter and the setup that I'd shown before in attaining mixed states, and we spatially separate them so that we incoherently add the two polarizations, so horizontal and vertical. And if we can control the intensity between the ratio of the intensities between the vertical and horizontal, then we can achieve mixed states based on the ratio between the intensities. And that's exactly what we did. So we split the input beam into two parts. And the first part, we convert it into total horizontal polarization and combine them using a beam splitter. So here we get horizontal polarization. And the second half, we convert it into vertical polarization and combine the two using a 50-50 beam splitter by spatially separating them by a bit. And then we use a neutral density filter to control the intensity differences between the horizontal and the vertical polarization. And like this, we can access different states on the Poincare sphere, and the target state can be a mixed state where the DOP is less than 1. And that is what we show. So this is the input Poincare sphere again, all the input states that we use. And we show that the target state here, in this case, is about 0.5, and here is about 0.3, and over here it's about 0.1. And this tunability is achieved by adjusting the intensities between the two polarization states, which is alpha in the setup. So this is the alpha, which is the intensity ratio. And as we tune the intensity ratio, we see that the degree of polarization changes from 1 to almost 0.1 or 0.2. And this measurement was done for various states. So we took 6 different input states and took the average, and that is how the error bars were obtained for this measurement. So the input state need not be a pure state, as was the case previously. It can also be a mixed input state where, so in our particular example, we have taken an input state of a degree of polarization of about 0.28. And then we tried the same setup. And as you can see, as you tune alpha, you see the tunability of the degree of polarization, and you can achieve any mixed state. Or you can, it's basically an, all polarization states are mapped into one particular polarization state, be it a mixed state or a pure state as an input, and you can achieve any state, be it a pure state or a mixed state in the target state. And so with this, we present simple optical setups for a all-to-one polarization mapping without the requirement of complex electronics or nonlinear media. The setup works for both, the setups work for both pure and mixed target states, as well as mixed and pure input states. And such a setup can enable accurate polarization control for single photons, as I had explained before, and ultrafast pulses as well, especially for partially polarized states. And now we are trying to access the degree of polarization as another degree of freedom for various applications in optical communication and biomedical imaging. And that's an ongoing study as of now. So I would like to thank you for your attention, and please feel free to ask me questions, or you can contact me on my email. Thank you.
All right. Thanks for your talk. Any questions for Ravi?
Yeah, maybe I will ask one question.
Sure.
So this is for single photon situation. This would be something like a non-deterministic situation.
Yes, you're absolutely right. So let me just go back to the setup. There are 50-50 beam splitters. So obviously, it's a non-deterministic thing. But whenever a single photon does come out in the right arm, you know that it is at a particular polarization. So it is still a many to one polarization mapping, but you do lose, of course, the probability of it coming out will be very less. And we calculate, I think it's 1/12 of the probability calculation. So you're right.
Okay.
Yes.
Okay.
But then the previous existing technologies, it's not possible because you always lose them in feedback, or you need high intensities. So for nonlinear medium. Yeah.
So even if this is a non-deterministic, it works for the single photons.
Yes. Yes. Yes.
Yeah, thank you.
Thanks.
Other questions for Ravi?
I suppose I have a question. Maybe if we went to the first scheme, you had like a first scheme with one sort of square, and then one with like two squares connected. But if we just go to the first scheme did it, right?
This one?
This one, yeah.
Yep.
So what is novel about this? You know, because if I've gone to an optical table and I literally just screw in a PBS and a half wave plate and a couple mirrors and a beam splitter, I guess, and then looks like you've got some quarter and half and quarter wave plates.
So that there lies the novelty, where it's a very simple experimental setup. And we were also confused that there is a disadvantage though, because it's an interferometer. So it is a very, it is very sensitive to like people walking and stuff like that. But still you achieve a target polarization state, and it's a all-to-one polarization mapping. So, but this particular setup is only for a pure state target and just using linear components. So.
Okay. What's the thing at the bottom? You said like a beam dump?
That's a beam dump. Yes. So, yes, so that is the next disadvantage of this setup. Thanks for asking. So you actually lose 50% of the light. But all the intensity, I mean, you don't lose out on the intensity. So basically, whatever the input state, the output intensity is the same for any particular input state, unlike a linear polarizer. But you lose 50%. And so we came up with another setup where you can actually have amplifiers, because here you attain a particular polarization. You can convert that to whatever your amplifier is phase matched for, and you can also have an amplifier here and then combine the two using a beam splitter. And so even when you lose out on these half of the intensities here and in both the interferometers, you can make up using amplifiers as well, if that is important in your experiment. So for especially in nonlinear optical experiments, since you want fixed input polarization for Chi2 processes, you would want high intensity along with fixed input polarization. And so this is a polarization stabilization as well. So even though the input polarization might fluctuate a little bit, the target polarization is constant. And then when you put that beam into a nonlinear phenomena, your phase matching remains intact, and you have a good conversion efficiency for your interactions.
Okay, so perhaps the interesting thing is you said that the output intensity is always constant.
It's always constant, yes. It's always constant, whatever your input polarization is. And it's not governed by any law like the Malus law for a linear polarization.
Okay. So that, all right. I don't know a whole lot.
Also the big advantage is that you can attain circular polarization, of course, the same using a SU2 transformation, but you can access even mixed states. So your input state can be a mixed state, or your target state can also be a mixed state. So it need not be a pure state. So it's a all-to-one polarization transformer in the true sense.
And so this was an experiment you actually performed? This is...
Yes. So these are the experimental results.
And it's a single photons? You send the photons through one at a time, or sort of
So
like?
all these experiments were done for like a laser beam, yes. Not for single photons.
Okay.
Yeah. But it can be extended to single photons, and that's what I said. We haven't tried that.
Turn the laser power down and it would be the same thing.
Yeah. But then, as Wong suggested, it will be deterministic, but it would still work. So yeah.
All right. If there are not any other questions, then thanks, Ravi. Thanks all the speakers.